Assalamu alaikum, everyone. Welcome to our webinar application of borehole image log. I am Abdullah Abdurrahman, business developer in Reservoir Solutions Company. Just I would like to present 5 minutes presentation about Reservoir Solutions. Reservoir Solutions is a company specialized in providing technical studies and courses for oil and gas companies and professionals. The company incorporates many professionals with diverse technical background related to oil and gas exploration and production. Our services include technical reservoir studies, field development planning, reservoir static and dynamic modeling, economic feasibility studies, technical support for academic researches like PhD and master degrees. Also, we are assisting in writing technical papers and publishing. We are providing technical petroleum courses by industry expertise, and we are providing mentorship programs. Just I would like to present our upcoming workshop, which is borehole image processing and interpretation. It will be 2-week hands-on experience workshop using software. The course package will include lifetime access to recorded sessions. So if you have time difference into your country, so don't worry about that. You will have lifetime access to the recorded sessions, and you will have also the course materials. Then you can ask an instructor even after the course. You will have datasets for application on software because our workshop is application-based. The course material will be provided. You will have open discussion with instructor during and after the course because we will have WhatsApp group for the course. So you can ask your question on the WhatsApp and the instructor will answer. At the end of the workshop, you will have a certificate with online identification ID on our website of Reservoir Solutions. We will learn into that workshop the application for borehole image log. You will do borehole image processing and quality control. You will do manual depth picking. You will interpret reservoir structure and stratigraphic. You will do structured depth analysis. You will learn also how to make depth azimuth vector output. You will calibrate the image interpretation by the core data. You will integrate the wireline logs with borehole image. So you will have integrated interpretation for all the open hole logs and also the borehole image. You will learn the porosity evaluation and texture identification. That is very important for carbonate reservoirs. You will do fracture characterization and interpretation, which will be very important into the production. You will learn for thin beds evaluation or texture identification and sand counting. You will do processing and interpretation of acoustic imaging. So if you are interested in interpretation and processing for acoustic and electric image logs like FMI, XRMI, OBMI, and so on, so you can do that by learning that into our workshop. The price for this workshop is only for students about $60, and for professional people is about $80. Okay, so don't miss that chance to join our workshop that will start on 10 of September. So you will have about 9 days to start our workshop. Thank you all. If you want to register for that workshop, I will send a link for registration into the Zoom chat. Also, you can know the details for that workshop and the content for that workshop. Also, I will send a link for the content for that workshop into the Zoom chat. About our today webinars, the structure for our today webinar is Engineer Osama Osman. Engineer Osama is a senior petrophysicist with about 12 years of experience in petrophysical analysis, core log integration, rock typing, and saturation height modeling. He also is experienced in borehole image processing and interpretation, NMR, and spectroscopy interpretation. For the webinar rules, if you have any question related to the webinar, please ask your question into the Zoom chat. Please mute your microphone and camera. In case that you wanted to have a certificate for attendance, you can fill into the form that its link will be sent into the Zoom chat. You will receive your certificate within 1 week. For upcoming courses and webinars, you can join our Telegram channel and you can contact us via email and WhatsApp. Thank you all for your attending, and Engineer Osama, you can start.
Hello everyone, I hope everyone are good and fine. Today our webinar will be borehole image application for oil and gas industry. The main question to ask ourselves, why using borehole image in our field development plan and exploration studies? Do we need to acquire borehole image in every well? Do we need to acquire borehole image in some key wells? I worked in a lot of fields. There are fields with no at all borehole image data, and there are other fields with a lot of borehole image data. We need first to understand and study the main applications of the borehole image to take the decision when to acquire the borehole image data. The first main application or structure interpretation. Borehole image can provide a very good answer for structure interpretation by determining a precise depth of subseismic faults, which these faults can act as a barriers and also can act as a non-sealing faults. And these faults can affect your development studies. I worked in several fields. There were some subseismic faults, and these subseismic faults acted as a barrier. So, for example, let's assume we have a water injector well, and this water injector well started to inject water to the nearby oil well, and there is a subseismic fault between these two wells. So, the injected water will not enhance the production of the nearby well because we have a subseismic fault acted as a barrier to prevent the flow of the water from the water flood from the water injector well to the oil well. How we can identify these subseismic faults? By using borehole image. Also, structure interpretation is related to fracture analysis. If you are working with a fractured carbonate and you are doing a formation evaluation for fractured carbonate, you can't do a precise formation evaluation for this reservoir without acquiring borehole image, because the borehole image will provide you with the fracture orientation, fracture porosity, fracture aperture, and that we are going to discuss in the next slides. So the borehole image is useful in the structure interpretation. It provides depths of subseismic faults. It helps in the fracture analysis. It provides you with a structure depth that can be helpful for the geologist and geophysicist for their maps. The second application is sedimentary analysis, and this is the most famous one. The borehole image is the second after the core data for providing a precise depositional environment. So the core is much more cost effective than the borehole image. You will not be able to acquire a core data in every well in your field. So you can acquire 1 or 2 cored well, and then you can acquire 3 or 4 borehole image data to have a precise depositional environment for the fishes model in your field. Also, it provides us with something that the core will not be able also to provide, the paleo current directions. You can acquire like 5 or 6 wells, and you determine the cross bedding of these wells, and you start to identify the channel trend, either a fluviatile channel, tidal channel, braided bores, tidal bores. So it will be useful to acquire borehole image for purpose of sedimentary analysis that will have a big impact on the fishes model. The third application is the textural analysis. It can provide a grain size analysis for clastic reservoirs based on resistivity of the borehole image, and we are going to see it in the next slide. So it's also useful for the texture analysis. The fourth application is the petrophysical application, where you can, from the borehole image, if you don't acquire a thin section data or a core data, predict the carbonate porosity type. You can know if you have a voggy porosity, if you have a touching vogs, if you have a VUGs connected with fractures. So borehole image can provide you in the carbonate reservoir with its texture and expected porosity type. Also, borehole image is very useful, and that I have worked a lot with it, the seabed analysis, especially in turbidite reservoir, deep marine deposits, tidal flats. The borehole image can provide you with the small seam beds of the sand and the small seam beds of the shale, and that will enhance your net reservoir computation. Also, it's very useful, and I used also this a lot, the secondary porosity quantification from the borehole image. You can, by using a quantitative borehole image interpretation, to determine the secondary porosity of your carbonate as a 360-degree in your reservoir, and this is very useful in carbonate field development plan. The last application is providing the directions of the induced fractures and breakout, which is very useful in the present-day stress analysis. So what is borehole image? What it means? Borehole image is very simple. It's a map of a certain property around the borehole. The property can be a resistivity, or acoustics, or density, or gamma ray, or photoelectric vector. And it provides a higher resolution compared with the other normal logs. You need to know that the borehole image as a logging tool provides the best resolution compared with all other logging tools. So borehole image is very important because of its resolution. We can categorize it into two types, wireline imaging and LWD imaging. The wireline imaging also have two types or two major domains, wireline resistivity imaging and acoustic imaging. In the next slide, we are going to discuss in details what is wireline resistivity imaging and acoustic imaging. Regarding the LWD imaging, its idea is little different than wireline. It's based on azimuthal measurement, which are focused on a sector of the borehole rather than average around the borehole. It provides you with information to distinguish the direction from which the feature approaches the borehole. Its idea is very simple. It's based on the bottom hole rotary assembly rotated with the sensors of the LWD to provide you either with resistivity at bed or gamma ray, which is called GVR, which is called GeoVision. It provides you with gamma ray imaging and resistivity imaging, and the PEF and the density imaging. So LWD imaging is very important. Also, wireline imaging is very important, and both have many applications that we're going to discuss now. But before talking about the idea or the theory of each borehole imaging, we need to know what is the tool choice, what information you need from this imaging. For example, let's say you have a formation. This formation characterized by strong resistivity contrast between the sand and shale, or it have a large grain size variation like we see in the turbidite or tidal deposits. In this case, it's not recommended to acquire the acoustic tool or the LWD tool. It's highly recommended to acquire the micro-resistivity wireline tool. It will be your first choice. Why? Because your challenge here will be the seam beds, or your challenge here will be the paleocurrent interpretation. In this case, the micro-resistivity imaging is number one for acquiring. So you are a GNG team, geophysicist, petrophysicist, geologist. You are sitting together and decide in the next well which borehole image you will acquire. You have a challenge of a big contrast between sand and shale, a large variation of the grain size, different channel types. So what comes to your mind is micro-resistivity wireline imaging. Let's say you have another type of reservoir in other well. You have a tight fractured carbonate. The tight fractured carbonate will have a large acoustic impedance between the fractured carbonate and the tight carbonate. In this case, the acoustic imaging will provide you with the best result. So you will acquire acoustic imaging instead of wireline micro-resistivity imaging. If you need an operational decision, like you want a real-time formation depth, in this case, wireline is not recommended, while the LWD imaging is highly recommended. So the G&G team will decide which tool to acquire in the reservoir, either a wireline micro-resistivity imaging, acoustic, or LWD. Also, you need to put in your mind the resolution, the effect of the resolution, whether the available tool have the vertical resolution to solve the geological concern, or the fluid type, water-based mud and oil-based mud, to decide, for example, micro-resistivity imaging, oil-based mud, which is OBMI or MRI, or water-based mud like XRMI and FMI. But as we know, every tool has its own limitations. Borehole images also has its own limitations. Let's say, for example, you drill the well, and this well is largely affected by a strong bad hole conditions. In this case, the borehole image is sensitive to the bad hole more than the other logging. So if the well suffer from strong bad hole, it's not recommended to acquire it, and you will decide that. Also, one of the limitations, the experience of the image analyst. You have an important well in your field, and this well you will make a decision about either fracking, perforating, development plan, static modeling. You can't deliver this well to someone who has 2 or 3 years only experience as an image analyst. You need someone higher than 5 years and worked with a lot of image data. So that one that's considered as a type of limitation for borehole images. The last part, and this part I worked with it a lot, the core image calibration. I worked with like more than 150 wells for borehole imaging. I had like 60 wells core data with image data, so I started to do core image calibration to identify the core lithophysis from here, for example, and compare it with the image lithophysis. Let's say we have here a cross-bedding, so the cross-bedding is clear in the core, and also it's clear in the image. You will take this image lithophysis and compare with the other wells which have borehole images, and you will do the coloration based on the image lithophysis, and that will be very supportive in your depositional environment interpretation. Also, this one like soft sediment deformation from the core, and also it's clear here from the imaging. So you can calibrate this image to the core and start to colorate the image lithophysis here with the other wells. The idea behind the electrical resistivity borehole image, its idea is very simple. The image are equipped with several number of pads or pads and flaps. We can see that this is the shape of the pad and this is the associated flap, and that is related to the FMI tool, for example. Every pad and the flap, you will see it have a row of buttons. This is the first row of button, and this is the second row of buttons. These buttons is responsible to emit an electrical current. After you drill the well and you insert the tool into the borehole, the logging tool will move up, and this pad will be in close contact to the formation. After it will be in a close contact with the formation, these buttons will start to emit an electrical current. This current will move through the formation and get back to the upper electrode. But take care, you have an insulating section to isolate the movement of the current from here to here. It needs to move from this place to the formation and get back to the upper electrode. Then you have an electrode here and you have an electrode here. You will measure the voltage difference, and then you can obtain the resistivity of the formation. For example, let's say the FMI tool. The FMI have 4 pads and 4 flaps. Each pad contains 24 buttons. So the total number of buttons in the FMI is 192. So you will have a 192 resistivity reading circulated 360 degrees around the formation at each depth. And this resistivity can be converted into a borehole image. And the difference in resistivity will reflect either the difference in the grain size or the difference in the lithology. And this is very important in the sedimentological and the structural interpretation. Regarding the acoustic borehole imaging, the acoustic borehole imaging, its theory is different. It's based on, we have a transducer. This transducer will start to send sound wave into the formation, and this sound wave will get back again to the same transducer. So the transducer will act as a transmitter and the receiver of ultrasonic pulses. The amplitude of the sound wave will be measured, and this amplitude will be derived as acoustic impedance and it will be converted into reflection coefficient. Then it will be extracted as amplitude image, defining the different acoustic impedance for different rocks. So we can see here something is famous called the breakout. It's very clear in the acoustic imaging because it have a high acoustic impedance difference with the nearby rock. While the transit time imaging also it provided with the acoustic borehole image, but its theory is different. It based on this equation, which is delta t equal 2d over the slowness of the mud. The acoustic imaging will provide you with a continuous log of the acoustic velocity of the mud, and you have the distance between the transducer face and the first surface of the received sound wave. By using the distance and by using the VMOD, you can obtain the transit time imaging. So the acoustic imaging is very useful in the stress analysis. It's very useful in the tight fractured carbonate, and it provides you with two main imaging, amplitude image and transit time image. After you process your borehole image, you need to understand the concept, and it's very important concept for every borehole image. It's called the manual depth picking. The geophysicist, for example, will import his seismic cubes and seismic lines to start picking the horizons and the faults. The image is something like that. After you finish your processing of the imaging, you will have an entire processed borehole image for the well, from the bottom of the well to the top of the well. So you will move from the bottom of the well to the top of the well, and you will start to do picking. But here, the picking is picking the feature, not picking the horizons or the faults. Let's see, we can see a feature here. We are going to pick, moving it by sinusoid shape. Here also, we are going to pick. Here also, we are going to pick. So this, for example, called dynamic imaging, which is obtained after the processing of the imaging, and this dynamic imaging after processing. This red and the blue is the apparent depth of the features or of the features, you are picking in your well. How you can pick this feature? The idea is very simple. You have this bed, which is inclined bed. How you can see it? By rolling up the well as 2D view, and when you see it like this, you will see an inclined plane. This inclined plane can represent, for example, a cross bedding. It can represent a fracture. It can represent an erosional surface or scouring surface. So you are going to pick this feature. How to pick? By moving or pointing at this feature. After you move on this feature, by using function, which is called tan -1, the amplitude of the sinusoid from here to here over the bit size, you will obtain the apparent depth value. And then by using the deviation and the azimuth, you are going to convert the apparent depth into true depth. And this is important to have either a structure depth or sedimentary depth or even fracture depth. All of these depthing are very important in your studies. So you need to understand the concept of the manual depth picking, and to understand that you need to do manual depth picking in the zone of interest or in the entire well to obtain different depth categorization. The applications we mentioned earlier, but here we are going to see some examples and to discuss it. For example, here a subseismic fault. This subseismic fault was resistive. What it means resistive? It appears as white color in the image. Resistive means it's high resistive, which means that this fault is cemented, which means that this fault is a barrier. So how we can determine that this is a fault? You will pick your feature. We can see that the true depth here is very low. Then the true depth will start to increase gradually, like here. This is analog and this true data. We can see that the depth start to increase until we see a peak with a clear resistivity different than the underlying bits, and then the depth will decrease again. So by using some analogs from reference and literatures, we can identify this type of faults. We can see that this normal fault with dragging. So also the image can support you with the type of the fault, can tell you if you have a dragging or not, if you have a barrier fault or a non-sealing fault. The second application is the fracture characterization and analysis. Yes, it can be considered a second application, or it can be under the structure interpretation. The fracture characterization and analysis, it's very important. You have the image data, you will pick your fractures. After you will pick your fractures, you will see these fractures in the tadpole track and then convert them into a stereo-net plot, a special Schmidt plot, and then see the strike of the fractures. After you derive the fracture orientation and the picking of the fracture, you can do some advanced workflow for the fracture characterization, which is called the fracture analysis. This workflow is under the categorization of quantitative image interpretation, not qualitative. Qualitative, just to obtain the depth of the fracture, the orientation of the fracture, and to mention if this fracture is open fracture or closed fracture. But the quantitative interpretation, it's very important in the fracture modeling, because you will derive a fracture aperture, a fracture density, and the fracture porosity. You need before this step to do something called image calibration, not core image calibration, something else called image calibration, where you are going to calibrate the borehole image data with the shallow resistivity from the triple combo. And we are going to obtain a high resolution curve called SRES. After we do the image calibration, we can determine the fracture aperture, the fracture density, and the fracture porosity. The sedimentary depth interpretation, here is an example of sedimentary depth interpretation. You will pick the formation, then you will identify a zone. Let's say you have, for example, a surface zone, or like deep turbidite zones, and this zone you want to see its direction of cross-bedding. So you will get this zone and plot it in a stereo-net plot and see the direction of the cross-bedding. But it's not necessary. The direction of the cross-bedding is the direction of a channel. The channel direction must be obtained when you penetrate the mid-axis of the channel and take its cross-bedding. But if you are in the flanks of the channel, the direction of the cross-bedding will be toward the main axis of the channel. It will not be the direction of the channel itself. So the sedimentary depth interpretation can provide you with cross-bedding by direction, for example, cross-bedding, which is something related to tidal system, image features analysis, as we mentioned before, core image calibration, and paleo current analysis. So all of these features can be obtained from sedimentary depth interpretation. We can see that the sedimentary depth interpretation alone can provide us with a lot of answers from the borehole imaging data. Moving next to the texture analysis. The texture analysis, its idea is very simple, but it's only work for clastic reservoir. It's based on the resistivity of the sand and silt and the clay. As everyone knows, in the image data, the resistivity of the sand is higher than the resistivity of the silt and the resistivity of the clay. So as the resistivity of the sand itself even increase, as the grain size increase, and as the resistivity of the clay decrease, as its grain size decrease. So we can, by using the quantitative image interpretation, convert the resistivity difference between sand and silt and the clay into a grain size analysis. And it's very important to study the grain size of your reservoir to see which zone has the higher grain size and lower grain size to have the biggest impact on your reservoir quality. The petrophysical application. The borehole image, as I mentioned, have a lot of applications regarding the petrophysics. First, the carbonate porosity type. You need to do the image processing and then start to see this feature. Do we have a vox? Do we have a fractures? What we have, we need to investigate it with the triple combo data. That's why the borehole image should be integrated with the wireline imaging, wireline triple combo data. You can't do a processing for the image and work with the image alone. You need to integrate it with the wireline triple combo. You need to integrate it with the sonic data if you have. You need to integrate it with the core if you have. So you will start to try to identify the prototype in the Carbonate by your experience or by calibration with core. Then you will, if you have a VUGs, you need to identify from the image the VUGs characterization. Do your VUGs are open, interconnected? Like open means it could be filled with oil. So the water-based mud will start to invade these VUGs and it displays the oil inside the VUGs, and it will be inside it instead of the oil. So the water will be appear as a conductive in the image. So when you see, for example, black circles in the image like that, it will be expected to be an open interconnected VUGs, or it also could be VUGs filled with pyrite. And the interpretation associated with the triple combo will help you to differentiate that, either if it's a VUGgy filled with pyrite or VUGgy carbonate interconnected. Also, you can have it as isolated, and that's very important in your reservoir recommendation. If you have an open interconnected VUGs, you don't need to do fracking. You just perf the zone and it will produce with the oil. But if it's an isolated VUGs, you need to do a recommendation that we need to frack this zone because the VUGs are not interconnected. Or sometimes you can face a problem that your VUGs is not open. It's a mineral filled, either with quartz cementation or calcite cementation. The other application also for the borehole image for petrophysics, by using the frequency with porosity, is determining a secondary porosity from the image. But this secondary porosity, it will be 360-degree porosity, not one directional porosity, because it's obtained from the image. How we can derive it? By a simple equation. But after we do the quantitative interpretation, we will derive the total porosity from the log, multiply the shallow resistivity, multiply the 360 conductivity imaging. After we multiply or use this equation, we can have a secondary porosity from the image. And this secondary porosity is not like the secondary porosity from the sonic. It's better. Why? Because it's a 360-degree porosity, which reflects the heterogeneity of your carbonate. But the porosity of the sonic, which is, the difference between the porosity from the neutron density and the porosity of the sonic is also secondary porosity. But this porosity is one direction only. But here, the secondary porosity from the image is a 360-degree. So you need to know that it's more important in your reservoir to have a secondary porosity from the image. The last part regarding the petrophysical application is sand counting, and it's famous, and I think everyone heard about it. Sand counting, you will identify by the difference in resistivity contrast between the thin sand and the thin shale, and you will count from bottom to up how many beds of sand you have, and you can determine the actual net reservoir in your well, instead of doing the triple combo interpretation, and you will have an underestimated net reservoir. And also this sand counting can be a calibration point for your raw resistivity pay model or seam-bed analysis. The geomechanics application. The borehole image is essential for any geomechanics studies because it provides you with the direction of induced fractures, and also it provides you with the direction of breakouts, where the direction of induced fracture is perpendicular to the minimum horizontal stress, while the direction of the breakout is perpendicular to the direction of maximum horizontal stress. So as we can see, the borehole imaging had a lot of applications in our reservoir studies, starting from structure interpretation, moving to fracture characterization analysis, sedimentary depth interpretation, texture analysis, petrophysical application, geomechanics application. And the best part about the borehole image, it provides different answers for every person in the G&G studies. It provides answers for the petrophysics. It provides answers for the geomechanics specialist. It provides answers for the geologist and sedimentologist. And it provides answers for the geophysicist, and also provide answers for the geomodeler, especially for fracture modeling. So I think my presentation is finished, and this is time for questions and answers. how you can QC or check the manual pegged features. It based on the experience. Like for example, let's say we have a shell dip, okay? And this shell dip, from the geophysicist, for example, he told you that we expected don't have any folding or dragging or anything. And then you picked a lot of shell points and you told me that you have a high shell dipping. You have like 50 degree for the shell. That's not reasonable because you are in a structure area which expected to have horizontal beds. Why you're picking for the shell is wrong. Also, when you pick the shell and these shells are related to each other, it prefers that they have the same azimuths. If you have different azimuths for the shell, that's wrong in the picking. Also, let's say how to QC a cross bedding. The cross bedding never exceed after the structure dip removal, never exceed 34 degree or 32 degree or 30 even degree because of the angle of repose during the deposition of the sediments. So when you tell me that I have cross bedding with 40 degrees, that's wrong. So this is the ways of quality control of your picking. Please, is borehole imaging different from wireline logging? Wireline logging include triple combo data. It can include sonic data. It can include NMR data. It can include formation testing and sampling. It can include even cased hole like production logging, like water RST, like CBL for cement evaluation. Everything related to logging is called wireline logging, either as an open hole logging or cased hole logging. Borehole imaging is one of types of wireline logging, or also one of types of LWD logging. LWD is called logging while drilling. While wireline logging, it is logging after you finish the well and extract the drill pipes. Then you will insert the tool to move from the bottom of the hole to the top of the hole. Structural dip removal and its impact on determining the paleo current. Structural dip removal is essential. You can, this is very good question. You can't take the dip directly and take this dip and put it in a stereo net plot and tell me that this is the direction of the channel, for example. You need to use the underlying shale, like this green picked is a dip of shale, and this red is a dip of cross bedding. Two approaches are present and are famous for doing the structural dip removal. The first approach is very simple by using the shale bed underlying the sand bed for removing the structure dip. Just subtract the dip value and also check the azimuth value of the shale compared with the sand. The other approach, it's called the set view, and it's based on something called the local curvature axis. It's based on something called the primitive circle and the grid circle, and you will determine the pool of every sedimentary depth, and then you plot it in the grid circle, and then after you plot it in the grid circle, you will take again this inclined bed and the new inclined bed, and after this new inclined bed, you will determine its pool to be the structure depth of your reservoir. So structure depth removal is very important and fundamental for any polycurrent interpretation. If you didn't do structure depth removal, all your interpretation is wrong. How can I know the fault from FMI image? Let's see. Okay. This is example, a clear example of a fault. Do you see that? This is a shale, high gamma ray, high neutron, low resistivity. When we pick this picking is horizontal. This is a horizontal dip, like the angle from 5 to 10 degree. Then this shale, you can see its depth started to increase. The shale is always deposited in a low energy environment. It is always deposited in a horizontal form. But when you see a shale with high depth, that means that this shale is subjected before to effect of a structure, either faulting, dragging, uplifting. It changed the actual depth of the shale. So we can see that this shale is the same like this shale, but this shale have lower depth compared with this shale, which means that the upper part of this shale started to enter a dragging zone. So we can see that the depth started to increase, but the azimuth is the same. Then we see a big a higher depth with a large feces exchange. We can see shale, and here a higher resistivity, which is, for example, silt or sand. Here it's silt. So we can see that the depth started to increase, a large contrast in resistivity here, and then the depth sharply decreased again. This point where the depth decreased again can be your fault. So from your experience, you can see that the depth started to increase, reached the highest point, and then decreased sharply again. You can compare it with analogs, or you can expect that here is a faulting. So this fault, you can identify also if it's a barrier fault or non-sealing. If it's a resistive fault, so 95% it will be a barrier. While if it's a conductive fault, like it's a black, it will be non-sealing fault. Let's see the other questions. What is the depth of investigation? The imaging always has lower depths of investigation due to its higher vertical resolution. When the vertical resolution increase, the depth of investigation decrease. So the image always read in the flush zone to the early or the starting part of the transition zone. So the image read in the flush zone. That's why the fractures appear conductive. Why? Because the fractures is originally filled with oil. After it's originally filled with oil, if you are drilling this well, for example, with water-based mud, the water will start to invade this opening and will make the oil get out of this zone, and it will invade this zone. And this water is a water-based mud, and it's conductive because it's saline. So it will appear as a black in the imaging, but the oil will not appear as a black in the imaging. I worked before with heavy oil, and I saw that the fractures wasn't black. It was resistive. But in that case, it wasn't resistive fracture, or it wasn't, sorry, cemented fracture. It was a fracture filled with heavy oil, because I knew from the background of the fields that we are producing from heavy oil. So when I did the borehole image processing and started to pick my fractures, I saw it as a resistive fracture due to the heavy oil can't be moved by the water-based mud. I hope that I answered your question. Is X-ray used for image logging? X-ray? No, I don't think so. No. What is used for image logging? Wireline micro-resistivity imaging, wireline ultrasonic imaging. For LWD, you have resistivity imaging, you have gamma ray imaging, you have density imaging, you have ultrasonic caliber imaging. You don't have X-ray for imaging. For borehole imaging, X-ray can be used for something called the CT scan or stuff like that, but I'm talking about borehole image logging. How to distinguish shallow faults from bedding like detachment faults? To be honest with you, I didn't saw detachment faults before. You can use an analogs from books or outcrops. When you open any published structure paper, you can see the shape of the dipping and to compare it with the shape of the dip you have. Like, let's see here. Here. How I did determine that this is this? By checking a lot of published paper literatures, and I found that this is the shape of the drag, analog shape of the drag, and it is exactly the same like I have. So I told my team that we have a normal fault with dragging along this well, because I compared it with analog. Always borehole image, you need to calibrate with core without crops. You need to see around you an analogs of structure faults or folding or reverse faulting or fractures. You can't rely on the image itself. You need to do a detailed study with analogs to obtain the best results that you can have. How can you differentiate the drilling induced fracture which influence the soil investigation zone from the formation fracture? That's also a very good question. Let's see how you can determine the induced fractures. The induced fractures is formed due to the drilling effect, where the tensile strength of the rock become lower than the overburden stress. So the overburden stress will start to make some artificial fracturing. But this artificial fracturing always have one trend, like the minimum horizontal stress will be perpendicular to the induced fractures. So the induced fracture will be formed at this side of the hole, and it will be formed at this side of the hole. If we measure the angle between this side and this side, it will be 180 degrees. So when you see the image, we can see there is a small a vertical crack here at this side, which is 0. And we can see a vertical crack at this side, which is 180 degrees. So when you see two vertical cracks, the difference between them is 180 degrees, you are expected that you're having induced fractures. But the natural fractures will be along the whole pads, all the pads you have, or at least half of the pads. You can see a conductive here, then this the bed increase, the conductive bed here, the conductive bed here, the conductive bed here. So you will pick this, and it will be along all the pads. That's no way can be an induced fractures because it's along the 360 degree of the formation. So it will be a natural fractures. I hope that I answered your question. Yes, we are going to show an example of that. Don't worry. Later we are going to show an example of how to compute the porosity image, by using the quantitative interpretation. It's a long step. First, you need to do processing. After the processing, you need to start your picking. Then you are going to do something called image calibration. Then after the image calibration, you are going to do the porospect module, which is an image based on the equation that we said, the image resistivity with, I think, Teclog, yes. So I think I answered all the questions, and I hope everyone have a good day and good luck. And anyone have any question regarding image, you can contact me in LinkedIn, no problem. Thank you, everyone. I think Teclog software. Thank you, everyone, and good luck, and have a good day.
Thank you, Engineer Osama, for this interesting presentation that covering the applications for borehole image data. So, and thank you for everyone for attending for our today webinar. Just I would like to remind you that if you would like to have a certificate for attendance for this webinar, just fill into the form that was sent into the Zoom chat. I will send the link again. And also, I would like to remind you that if you want to register for the upcoming 2 weeks workshop for borehole image processing and interpretation, you can also register by the links that would be sent again for the Zoom chat. Thank you again, and hope you good night, inshallah.